So let me start by thanking everyone for being at this presentation, giving you a good morning, and thanking the organization for accepting my talk. And today, like I said previously, we're going to talk a little bit about service meshes in general. We're going to talk about Istio in particular, and we're going to see some of the common use cases for a service mesh, and how Istio handles some of the common issues that service meshes can bring to the table. So we're going to just give a quick introduction about microservices and some of the challenges that microservices present when we onboard that kind of architecture. We're going to go through what a service mesh is, and then we're going to see Istio on the perspective of traffic management, security, and observability, and how we can actually onboard those kinds of functionalities. So let us start by looking at microservices. So in this era of digital transformation, we are in a relentless pursuit of better serving our customers and users in general, right? So developers not only need to evolve into faster development cycles and use agile principles, but usually we also require vastly faster deployment times. So no longer deployment, even if it's just like clicking a button or running a script of a monolithic application, like once a month or once a quarter is sufficient. We need to reduce that to shorter cycles, probably several times a day. So the way that the industry at large started to implement architectures to seek out this vision is by breaking our big applications, our monoliths, into smaller units, so that smaller teams can actually have independent workflows, have different governance models, and deployment pipelines for each of those services. So, and this is usually defined as a microservices architecture. So, why do we do this? Why do we actually use microservice architecture? So, we usually do this for several reasons. Some of those are these ones that are described here. So, we want services to be more maintainable. So, we want a whole service to fit within our comprehension, so we can actually maintain that service. And of course, it becomes more scalable. So it's smaller, we can scale it, for example, horizontally, without having to scale the whole system at large. Services are also loosely coupled, so we can actually do changes to one service without impacting how our other services are being affected. They can be deployed independently, so I can do changes on service A and don't need to change on service B, and we can evolve services independently. Of course, we can organize business capabilities around these services, so we can have focused smaller teams that actually handle business capabilities focused around these microservices. But is it all sunshines and rainbows, like I usually say? So by migrating from a monolith to a microservice architecture, we gain a lot of benefits, but we also introduce some new things that we now have to think and consider. So we need to think about service discovery. Now that application functions are split into different services, they need a way to find each other and communicate to make service calls. We also need to handle load balancing, because each service can scale independently and needs load balancing between different instances. We need to be fault tolerant, so that one service shouldn't halt the whole business. So we need to build built-in resilience measures. We also have the need now for distributed testing. So we need to understand how services are interacting with each other, how long they're taking to perform certain tasks, and if an error happens, what is generating that error. And of course, we need metrics like we used to, but now each service needs to export metrics in a consistent way, and we need the ability to relate those metrics with each other. And of course, we need security. We need to employ authentication, we need to employ access control, we need to employ encryption to ensure that our systems are secure. So each service will need to address and implement these features independently. And they need to do it no matter what the programming language or the framework that we are using. To achieve this, we can, of course, use libraries that implement them in each service. But this means that we have to develop and evolve and maintain those libraries for each technology stack that we use. And we need to ensure that all development teams are using the correct versions. So let's start by building a few concepts in order to achieve to understand what a service mesh is, and then we'll see how a service mesh can address some of these issues. So essentially, what is a mesh network? So the premise for a service mesh. So a mesh is essentially a network topology in which infrastructure nodes don't have specific roles, and they can interact with each other without those specialized nodes to perform tasks. They will get their information to know what to do and how from somewhere, some sort of central system or some sort of distributed system where they get information. But the main idea here is that nodes can connect to each other instead of passing through specialized nodes to perform certain tasks. So this is, on a very high level, the concept of what a mesh network is. Another important concept for a service mesh is the concept of the sidecar proxy. And this is the combination of two concepts, the concept of the service proxy and the concept of the sidecar pattern. So the proxy will be something where all the traffic coming in and out of a service will go through. So a service proxy is essentially an application service or an application where services rely for additional capacities. So on that proxy, we can put things like automatic retries, timeouts, circuit breaking, service discovery, and a lot more. The other important concept is the concept of the sidecar pattern. So the sidecar is a service that is attached to your main service, and it has the exact same life cycle as the main service. So if the main service goes down, the sidecar goes down. So if the main service goes up, the sidecar goes up. This is usually known as a decomposition pattern. In some literature, it's also known as the sidekick pattern. So this is more or less how the sidecar proxy looks like on an infrastructure. So we have our main services. The sidecar proxy will be alongside the service itself, and all traffic coming in and out of the service will pass through the proxy. So using these two concepts, what is essentially a service mesh? So a service mesh takes away all the complexity part by using a proxy. So all those features that we saw that we would require to be employed on a microservice architecture can be abstracted on that proxy. Services can focus on running business logic and allow the service mesh to handle things like service discovery, routing, and tracing. So the service mesh will effectively be the connective tissue between all of our services and will add those additional capacities. So those, like we've seen previously, those capacities will be offloaded to the proxy, and at an application level, we will only focus on differentiating business logic. In practice, how does a service mesh look like? So usually a service mesh has two main components. The control plane, which consists of a set of services that provide administrative functions over the service mesh. Users will usually interact with the control plane by using a CLI or an API to configure the service mesh. For example, if we are administrators, we can define routing rules, circuit breaking rules, we can configure observability, or even enforce access control through the control plane. The data plane will be composed by our services alongside the proxies, what we see, the sidecar proxies. Those proxies will sit alongside the services themselves, and all traffic, both ingress and egress, will flow through them. And they will be the ones that will be responsible for actually implementing all those features that we've seen. These proxies will get their configurations from the control plane and can export metrics, traces, and logs directly to some external service or through the control plane itself. Many of these features, the features that we need to function, are at request level, and so the sidecars can work as a layer 7 proxy. This will allow them, for example, to load balance intelligently between based on service latency or retry requests upon failure. Also, the sidecars will add functionality at the connection level. For example, sidecars can implement TLS connections, allowing both sides of the connection channel to validate each other's TLS certificates before communicating. So this, on a high level, is what a service mesh is. But what is Istio? Istio is essentially an implementation of the what we've seen of what a service mesh is. So Istio provides behavioral insights and operational control over a service mesh as a whole, and offers a complete solution to satisfy diverse requirements of our microservice applications. With Istio, we want to add all those capabilities that we've seen before, like authentication, mTLS, routing, circuit breaker, and much more. Istio is also designed for extensibility and meets a wide range of deployment needs. If you look at the high-level architecture of Istio, we can see that it's very similar to what we've seen on the previous architecture. So we have the control plane and the data plane. In control plane, we have a component called Istiod, which has several components inside that will handle discovery, configuration, certificates, and much more. And of course, in the data plane, we have our services alongside the proxy, which in case of Istio will be the Envoy proxy. So what is the Envoy proxy? It's a high-performance proxy. It's developed in C++, and it was built at Lyft. It is deployed in Istio as a sidecar to the relevant services on the same Kubernetes pod in case of a Kubernetes architecture, which is what we are going to focus on this presentation. This type of deployment will allow Istio to extract a wealth of signals about traffic behaviors and attributes. And of course, Istio can turn these attributes into enforcement policies. The sidecar proxy also allows us to add Istio capabilities to an existing deployment without the need to re-architect or rewrite code. So this is one of the big premises of the service mesh, is that we can add and remove functionality with that without having to actually change anything in our application code. Istiod is Istio's control plane. It provides discovery, configuration, and certification management. Its main goal is to convert high-level rules into something that Envoy proxies understand. We usually interact with it via its management API, via the API directly or through a CLI. It possesses security features for service-to-service and end-user authentication and authorization. And it can also act as a certificate authority and generate certificates for mutual TLS. So now we're going to start to see all of these features that Istio can provide and see how some code examples of how we can implement them in Istio. And the first one that we are going to see is traffic management. So traffic management in Istio is essentially traffic rules that control traffic between services. They aim to make our life easier by allowing us to define things like timeouts, retries, circuit breaking, A/B tests, canary rollouts, and so on and so forth. These kinds of patterns are patterns that companies like Netflix, Amazon, or Facebook, just to mention a few, have been using for years. Istio also has out-of-the-box failure recovery features that allow us to make our service more robust against failures of dependent service or even the network. So the first concept that we're going to see about traffic management in Istio is the virtual service. So what is a virtual service in Istio? So a virtual service is essentially how requests are routed to a service within the mesh. It is a set of rules that are evaluated in order and that allow Istio to match each given request to its real destination. So going through the code, we see that we have a few sections here. So we have the host section, which are user addressable destinations. These are the addresses that the clients will use when they will send a request to a service. We have the HTTP section, which are virtual services routing rules, and they describe the match conditions and actions for routing. A routing rule consists of a destination where we want to send traffic to and 0 or more match conditions, and it will of course be dependent on the case. So in this example, the first routing rule has a condition, and so it begins with the match field. In this case, we want this routing to apply to all requests for the user M is Ricardo, so we use the header and user and the exact field to select the appropriate requests. And at the end, we have the routing section. This field specifies the actual destination for the traffic that matches this condition, and it has to be a real destination that exists within the Istio service registry, or else Envoy won't know where to send traffic to. And of course, we can have a default rule at the end. We can also have multiple match conditions or multiple match blocks, making it as complex as we want. We can, for example, distribute traffic by weight, like we are describing here in the example. So here we're saying that block V1 will get 75% of traffic and block V2 will have 25% of traffic. We can also use routing rules to perform some access on the traffic. For example, if we want to append or remove headers or rewrite some URL. The next concept that we're going to see is the concept of the destination rule. So if we go back, virtual services are how we route traffic to a given destination. And destination rules are what happens to that traffic once they're at some destination. Destination rules will be applied after a virtual service has applied its routing rules and are evaluated so that so these rules will be applied to the real traffic at the real destination. We use destination rules to specify named service subsets, for example, as grouping all of a given service instance by version that we can be used in the routing rules or virtual services. On a destination rule, we can define things like load balancing. By default, Istio will use round robin, but we can define things like random, weighted, or list requests. Each subset of services is defined based on one or more labels, which in Kubernetes are key value pairs that are attached to objects such as pods. So if we look at this example, we can see that we have a simple random load balancer for the V1 and V3 subsets. And the V3, of course, will be the default load balancing. On the V2 policy, we see that we are defining a round-robin load balancer. Next, we have the concept of a gateway. So a gateway is used to manage inbound and outbound traffic into the service mesh. It will be applied to standalone Envoy proxies that will be running on the edge of the mesh. They are primarily used to manage ingress traffic, but they can be used to also manage egress traffic. And they allow us to configure dedicated exit nodes for traffic leaving the mesh, limiting which services can or even should access external networks. And they will enable secure control of egress traffic. If we look at this example, we are defining, it is letting HTTP traffic for mcccricardo.com into the mesh on port 443. But it doesn't specify any routing to that traffic. It only allows the traffic coming in. To specify routing and for the gateway to know where to send the traffic, we must bind that gateway to a virtual service that we've seen previously. And we do this by using the virtual services gateway field. We can then configure the virtual services with the routing rules that we've seen previously. Another important concept of traffic management in Istio is the concept of a service entry. And a service entry is used to add a service to the registry that Istio maintains internally. This means that after we add a service to the service entry, the Envoy proxies can send that traffic to those services as if they were part of the mesh itself. Configuring service entries allows us to manage traffic for services that can be running outside of the mesh and treat them as if they were part of the mesh itself. This means that we can add those functionalities that we've seen before, like timeouts, retries, and fault injection, like the services were part of the mesh that we are defining. We can also add services from different clusters to the mesh, and we can then, in this way, configure a multi-cluster Istio mesh on Kubernetes. We don't need to add a service entry for every external service that we want in our mesh, because by default, Istio configures the Envoy proxies to be passed through. However, we can use Istio's features to control traffic to destinations that aren't registered within the service registry. For example, in this destination rule, we are enforcing the use of mutual TLS to a service defined in the service entry that is external to the service mesh. And of course, many of the things that we have to deal on a day-to-day basis are things like timeouts, retries, and circuit breaking. And this can be added to the configurations that we've seen before. So on a virtual service, we can define, for example, that we have a timeout of 10 seconds for every request that goes into block V1. We can also define retry rules. So if a request fails, we are saying that we want that request to be retried 3 times, and we want Istio to wait for 2 seconds between each retry. And on a destination rule, we can define circuit breaking rules. So in this example, we are defining that will only allow a maximum of 100 connections for the specific version of the block. And last but not least, Istio has support for chaos engineering. So in Istio, we can inject two types of faults, and they will both be configured in the virtual service. We can inject delays, and delays are timing failures. They mimic increased network latency or an overloaded upstream service. And of course, we can inject errors. So these kinds of errors are crash failures, and they usually mimic a failure in an upstream service. These kinds of crashes usually manifest themselves in the form of HTTP error codes or TCP connection failures. So we can use these chaos engineering practices to actually test our systems, see how reliable they are, and we can actually use them also to test the virtual service and destination rules that we've defined previously. We'll now focus our attention a little bit on security and how Istio implements some security features within its mesh. So breaking down a monolithic application into atomic services offers various benefits like we've seen before. They include better agility, better scalability, and better ability to reuse services. However, microservices also have particular security needs. We need to defend against man-in-the-middle attacks, for example, so we need traffic encryption. We need to provide flexible service access control. So things like mutual TLS and fine-grained access control policies are required. And we also need, of course, to determine who did what and what time. So we need auditing tools. So Istio Security provides a comprehensive security solution to solve these issues. In particular, Istio Security mitigates both insider and external threats against our data, endpoints, communication, and the whole platform. Istio Security provides strong identity, power policy, and transparent TLS encryption and authentication and authorization, also known as AAA, tools to protect our services and data. On a high level, this is how Istio Security looks like. Security in Istio involves multiple components. We have a certificate authority that will be responsible for key and certificate management. It will have a configuration API that distributes information through the proxies, authentication policies, authorization policies, and secure naming information. The Sidecar and perimeter proxies will work as policy enforcement points to secure communication between clients and servers. And a set of Envoy proxy extensions will be used to manage telemetry and auditing. The control plane will handle all the configuration from the API server and configures the policy enforcement points in the data plane. And of course, like we've seen, the policy enforcement points will be the Envoy proxies. So basically, Istio Security will be going to see now is composed of its two main components, the authentication and the authorization part. So Istio provides two types of authentication. The first one is pure authentication, and it's used for service-to-service authentication, and it's used to verify that a client making a connection. Istio offers mutual TLS as a full-stack solution for transport authentication, which can be used without requiring any service code changes. And we also have request authentication, which is used for end-user authentication to verify that the credential attached to requests. Istio enables request-level authentication with JSON Web Tokens validation, and it offers a streamlined developer experience using custom authentication providers like OpenID, for example, Auth0, Firebase Auth, Google Auth, and so on. In all cases, Istio stores the authentication policy in the Istio configuration store via the Kubernetes API. Istiod will keep them up to date for each proxy, along with the keys where appropriate. Additionally, Istio supports authentication in a permissible, which will help us understand how a policy will change and can affect our security before it will actually be enforced. So now we're going to see an example of peer authentication and request authentication, how they are implemented in Istio. So Istio tunnels service-to-service communication through the clients and through the policy enforcement points, which are implemented as the Envoy proxies. Mutual TLS has a permissive mode, which allows a service to accept both plain traffic and mutual TLS traffic at the same time. This feature greatly improves the mutual TLS onboarding experience. In this example, we have an authentication policy that specifies that transport authentication for workloads with the label app log need to use mutual TLS, or else the communication will not be allowed to go forward. Next, we have an example of a request authentication. So request authentication defines what request authentication methods are supported by the workload itself. It will reject a request if the request contains invalid authentication information or even is missing the authentication rules at all. A request that does not contain any authentication credentials will be accepted but will not have an authentication identity. So this allows us to actually restrict requests to workloads. So in this example, it requires a JWT token for all requests for workloads that will arrive at a block. The second component in security will be authorization. So Istio provides authorization features at the mesh, namespace, and workload level, and provides access control for all workloads within the mesh. The authorization policy enforces control to all inbound traffic in server-side Envoy proxies. Each Envoy proxy runs the authorization engine that authorizes a request at runtime. When a request comes to the proxy, the authorization engine evaluates a request against the authorization policies and returns the authorization result, which will be either allow or deny. We don't actually need to explicitly enable Istio authorization features. We just need to apply an authorization policy to the workloads where we want to enforce access control. For workloads without authorization policies applied, Istio doesn't enforce any access control and will allow requests to pass through. So in this example, we have a policy that allows traffic only from the namespace development. In other words, we are isolating the namespace from other namespaces. And we are saying that we are enforcing mTLS also. So in this example, we have configured peer authentication to be strict, but we want to make sure that the traffic is indeed protected by mTLS with an extra check in the authorization layer. This is also known as defense in depth. So this policy denies the request if the principal is empty. The principal will be empty if plain text is used. In other words, the policy allows requests if the principal is non-empty. An asterisk means non-empty match and is using the not principal, and using the not principal means that matching on an empty principal. Another example of authorization policy we can see here by using JWT validation, which is common in an ingress gateway, and you may want to use different JWT issuers for different hosts. We can use the authorization policy for fine-grained JWT validation in addition to the request authentication policy. Using the following policy, we can allow access to the given host if the JWT principal matches. Access to other hosts will always be denied. And we'll now go to focus on our third component that we've seen that Istio can help us with, which is observability. So Istio generates the following type of telemetry in order to provide an overall service mesh observability. One of the components that it has is metrics, and Istio generates a set of service metrics that will be based on the four golden signals of monitoring, namely latency, traffic, errors, and saturation. Istio also provides detailed metrics for the mesh control plane. A default set of mesh monitoring dashboards are built on top of these metrics. Istio also provides distributed tracing. Istio generates distributed trace spans for each service, providing operators with a detailed understanding of the call flows and service dependencies within the mesh. And of course, Istio provides access logs. As traffic flows into the service mesh, Istio can generate a full record of each request, including source and destination metadata. This information will enable operators to audit service behavior down to the individual workload instance level. So regarding metrics, metrics provide us a way of monitoring and understanding behavior in aggregate. To monitor service behavior, Istio generates metrics for all services, for all service traffic in and out of the service mesh. These metrics provide information on the behavior such as the overall volume of traffic, the number of errors, and response time for requests. In addition to monitoring the behavior of the services within the mesh, it's also important to monitor the behavior of the mesh itself. And as such, Istio components export metrics on their own internal behaviors to provide insight on the health and function of the service mesh control plane. Istio metrics collection begins with the sidecar proxies, and they are called the proxy level metrics. Each proxy generates a rich set of metrics about all the traffic passing through the proxy, both inbound and outbound. The proxy also provides detailed statistics about the administrative functions of the proxy itself, including configuration and health information. And Istio provides a set of service-oriented metrics for service communications. These metrics cover the 4 golden signals that we've seen previously. And last but not least, Istio control planes also provides a collection of self-monitoring metrics. Another important component in microservices architecture is the ability to observe services, the platform as a whole, and as such, distributed traces are of the utmost importance. Distributed tracing provides a way to monitor and understand behavior by monitoring individual requests as they flow through the mesh. This feature empowers operators to understand service dependencies and the sources of latencies within the mesh. Istio supports distributed tracing through the proxies. The proxies will automatically generate traces on behalf of the applications that they are proxying, and they only require that the application forward the appropriate requests, and that's usually some headers that need to be configured. Istio supports a lot of tracing backends, which include Zipkin, Jaeger, Lightstep, and Datadog. Operators can control the sampling rate of trace generation. This is the rate at which tracing data is generated for each request. And this allows operators to control the amount of data and the rate that the tracing data is being produced. In this example, we are seeing an integration of a trace that is done between Istio and Zipkin. And the last piece on observability is the concept of logs. Access logs provide us a way to monitor and understand behavior from the perspective of an individual workload instance. Istio can generate access logs for service traffic in a wide range of configurable formats, providing operators with full control of how and what and when we are logging. And of course, Istio can do a lot more. We can have things like multi-cluster mesh, we can have WebAssembly extensions, we can have custom Envoy filters, DNS proxy, and a whole lot of things that Istio supports. But before I let you go, is it again all sunshine and rainbows? Of course not. So whatever type of architecture or solution that we try to import in our system, it all comes with some caveat attached to it. So there's no silver bullet that solves all of our issues without bringing some type of caveat along with it. So we have to deal with a lot of things when we onboard a service mesh in general or an issue in particular. So some of those are complexity. So service meshes add new components to our overall solutions architecture. So irrespective of what service mesh product we choose, we always have to manage an extra set of services, the control plane services, as well as configuring the sidecar proxies for each service. We also have to take into consideration resource consumption. So the sidecar proxies use resources like memory and CPU, and that will scale linearly, mostly in the case of the proxies with the amount of service that we have. Of course, this also has some cost attached. So apart from our product, the cost that our proxies services have to run, we have extra computing resources that need to be taken into account because of the proxies and the service mesh control plane, and that also has a monetary cost. We also have an extra network hub. So although the sidecar proxies offer a lot of functionality, they add an extra network hub for services when it needs to communicate to another service. So that needs to be taken into the consideration. And of course, debugging distributed systems is complex. So adding more services within the mesh can make the process even more complicated. And that's it for my part. I think I hope the presentation gave you a good overview of what a service mesh is, how it is architected, what are its main components, what are some of the features that a service mesh has and provides, and I hope it gave you a glimpse in some of the main components that Istio also brings with it, and some of the things that out of the box Istio allows us to do. Of course, Istio is extensible. It supports a lot more than we just seen here. we just focus on the main things that we can onboard and the easiest things to onboard. So I hope this was a good introduction to Service Mesh and Istio, and thank you so much for attending this talk.
Hi, Ricardo, one more time. Thank you so much for your speech. And I invite you to join our discussion table to answer the questions from our participants. And dear participants, don't hesitate and ask your questions. Feel free to discuss everything with Ricardo. Thank you so much.